Pipelines are a super important concurrency pattern in Go, but there's a bunch of nuance around how they're actually implemented. So this video will slowly build up to the best version of a pipeline implementation, in my opinion. So let's get started. The general idea behind a pipeline pattern is to have a series of functions that each act like a stage in a data processing workflow. So the first function is called the generator, and it's responsible for creating or loading the data from an external source. It will return a channel that the generated data will be sent to. Then the rest of the functions each accept a channel as an input and return a channel as an output. And the most important point here is that each stage of the pipeline will be running in its own Go routine. So we'll start with a simple generator function that will continuously produce random numbers. It will accept a context and returns a read-only int channel that can be consumed by subsequent stages in the pipeline. So first, we make our output channel. Then we spin up the Go routine for this step in the pipeline. And inside the Go routine, we use the for select loop that I talked about in my last video. And if you want to watch that, links in the description. And we'll have two cases. The first case will exit the Go routine if the context is canceled. And the second case will send to our output channel just a random int. Then we also have to defer closing the output channel. And lastly, we need to return the output channel. Simple generator. So now in the main function, we have a context that will be canceled after 2 seconds, and we can pass that into the generate function and get a channel out. So now we need the next stages in the pipeline. So let's say we have a square stage and a double stage. They both accept a context as an input, as well as a receive-only input channel. And then they'll return a receive-only output channel. So these functions will be responsible for starting Go routines that will handle the input coming from the input channels and then publish the result to the output channels that are returned. And the actual function shape looks very similar to the generate function. So we make our output channel. Then we start a Go routine. And in the Go routine, we're going to defer closing the output channel and do the for select pattern. And we'll have the same context case as in the generate function, but the second case is where things change. So we're looking for the value coming from the input channel. And when we get that, we want to process it. So the square function is going to square the value and then pass the results to the output channel. And I'll add a quick print line for visibility and a sleep just to slow this down a bit. Cool. Then last, we just need to return the output. So this looks almost identical to the generate function, and all of the subsequent stages will follow this exact pattern. So we can just copy and paste this into the double function, and instead of squaring the value, we're going to double the value. Now back in the main function, we can finish composing the pipeline. So the second channel comes from the output of the square step where we pass the context and the previous channel in. And then the next channel comes from double. And again, we pass the context and the previous channel, which is now channel 2. So data is flowing from channel to channel, but being transformed at each stage of the pipeline. So the last thing we need to do is handle the output of the final channel. And an easy way to do this is to do a range loop over the channel. And then we'll just print the value. So this loop will execute until channel 3 is closed. So once the context cancels after 2 seconds, each Go routine that's launched by our functions will know it needs to exit and then the channels will all be closed, at which point this will exit and the main function will finish. And I realized I didn't change this here. So now when we run this, we should get all the output that we expect. So each stage is executing where we're squaring the inputs and sending it to a new channel. Then it goes to the doubling stage where we're doubling the inputs. And finally, we range over the last channel and get the final output of the pipeline. So this is a basic pipeline, but there are a couple tricky issues that are a little non-intuitive that we need to deal with. The first problem is what happens when an upstream channel is closed before the context is canceled. When a channel is closed, Go will broadcast the 0 type for that channel to every Go routine waiting on a receive. So let's say we're blocked in this select statement, waiting for either the context to cancel or for a value to come in from the input. If the input channel gets closed, then the value here will always be equal to 0 because that's the 0 type of an int. This is a similar issue to one I showed in the last video, link in the description, but has different consequences in a pipeline and a slightly different solution. So the real problem here is we might be treating an erroneous 0 value as real data in our pipeline instead of ignoring it. So let's throw together a quick example to demonstrate. So in the main function, we're going to loop, let's say 20 times. And on each iteration, we'll create a cancelable context and make a channel. Then we're going to call cancel immediately and close the channel. And then we do our select statements. And we have 2 cases. First, we're waiting on the context to cancel. Then we're waiting on the channel to close. Intuitively, because you call cancel first, you would expect that this case gets selected. But what actually happens is Go will select a random case because both of the cases are ready to go. So when I run this, we should get a mix of cancel and closed. So it's just random every time. And this applies no matter what order we're doing it in. So if I close the channel first, we get the same results. Some are closed, sometimes the cancel gets called. The fix for this is way easier than actually understanding the problem. So back in our pipeline, whenever we are reading from an input channel, we also need to check if that channel is closed. And if it is closed, then we'll return and exit this stage of the pipeline. So again, if an input channel coming from upstream gets closed before the context is canceled, then we return from the Go routine and ignore any of the 0 value data that's coming from a broadcast of the input channel being closed. So again, super easy fix to a little bit of a non-obvious problem. All right, the next issue happens when we send a value to the output channels. Right now, the select statement in the square and double stages waits on 2 channels, the context done channel and the input channel. So this will block execution until one of those channels sends a value. Now in the second case, we're sending a value out to another channel, which we also know is a blocking operation. And that's where the problem happens. To unblock the send operation, the next step in the pipeline needs to reach its receive point. But if the downstream stage stops accepting new values from this channel for some reason, then this send will never be unblocked. And even when the context is canceled, if we're already inside this case, we won't run through this case and exit the Go routine. And all of that can lead to a Go routine memory leak at the best and a deadlock error in the worst case. So to actually demonstrate this issue so you can actually see it, I inlined the pipeline into the main function. So now we have a wait group. We have our same context that's going to cancel after 2 seconds. And then we do everything inline here. So we have our first stage that generates a random int and sends it to channel 1. And then we have our second stage, which accepts values from channel 1 and then squares them and sends them to channel 2. Then instead of ranging over channel 2, I'm just receiving from it once. So after receiving the first value, we're going to stop reading from channel 2, which will block this send. And that should cause us to hit a deadlock. So if I run this, get the logs, and then deadlock. So that's the issue. Now there's a simple but annoying fix for this. Instead of sending a value directly to channel 2, we're going to do a nested select statement. And our cases, again, are waiting on the context to cancel or waiting on the send operation to complete. So now, even if the downstream stage stops receiving values from channel 2, we won't block forever because we're in a select statement with the context case, and that case can still execute. And if I run this, we should get the same output with no deadlock errors. Perfect. So this is what the original pipeline looks like when we're handling block sends and closed channels. So whenever we receive from a channel, we check if that channel is closed. And then whenever we send to a channel, we wrap it in a nested select statement. But if you have a lot of pipeline stages, this can be a lot of repeated code. And if you get confused looking at all this noise like I do, you should definitely subscribe for more videos explaining confusing nonsense like this. So now to fix all this noise, I like using a couple of helper functions, one for sending to a channel and one for receiving from a channel. The first one we'll do is called CancelOrSend. And it is going to have a single generic type and accept a context and the input channel you want to send to and the value you want to send to the input channel. And then it will return true if the value actually gets sent to the channel and false if the context got canceled. So the implementation for this one is super simple. It's literally just the nested select statement that we had before. And we are going to return false here and true here. And we're sending the value to the channel that got passed in. And now in our stages, we can replace this nested select statement with a call to CancelOrSend. And we pass the context, the output channel that we want to send to, and the value, which is square here. So if the context gets canceled, we're returning. And we'll do this with all the different spots where we are sending a value to a channel. So that cleans this up a little bit. And now if I run this, everything should work as we expect. Cool. So we've handled the inner nested select statement, but we still have the outer select statement that is used for receiving values from the input function. So we should handle that next. So let's make another helper function. And in the concurrency in Go book and other blog posts, this helper is usually called OrDone, but I hate that name. So I'm going to call it CancelOrReceive. There are actually two ways to implement this function. So I'll show you both the official way and the way I like better. So first, the official way. We have one generic type and it accepts a context and a receive only input channel. And in this official implementation, it also returns a read only channel. The reason it returns another channel is so you can range over the values in the input channel without worrying about the cancellation logic from the context. So first we create the new channel to return. Then because we're returning the channel from the function, we need a new Go routine that will handle sending values from the input to the output and handle the cancellation logic. So the Go routine will follow the exact same pattern we've been using in all of our transformation steps in the pipeline. We do the deferred close, then we do a for select, and we're selecting on the context being canceled and receiving from the input channel. So we do our receiving logic. If the channel is closed, we're going to return. And then we need to send the value to the output channel. And again, when we send, we need to wrap that in a select statement or use our other helper function that we did before, CancelOrSend. So we can go if not CancelOrSend, pass the context, the out channel, and the value. And if it cancels, we're going to return. And last, you return the out channel. So now in our actual pipeline function, instead of using a for select loop, we can do a for loop on the range of the channel we get from CancelOrReceive. And we'll pass in the context and the input channel. So we no longer need this check, but we still need all of this. Cool, so that slimmed down the function a bunch. And the reason this works is because when the context is canceled, the channel returned from CancelOrReceive will be closed. And when you close the channel, the range loop will exit. And then when you exit, the go function will return. So this implementation works, but again, it's not the one I like to use. Go routines and channels are lightweight to spin up, but I still don't think you need to overcomplicate this by spinning up yet another nested Go routine and starting yet another channel. So my preferred implementation has the same definition, except it doesn't return a channel. Instead, it returns a value of type T or a Boolean. The value return is the value that you receive from the input channel. And then the Boolean that's returned is used to tell you if the context is canceled or the input channel was closed. So if either of those are the case, then OK will be false. And because we're not spinning up a new Go routine, the implementation is super simple. We do a select. And again, you're probably sick of this pattern. We have two cases. First case is when the context completes and we return. And the second case is when we get a value from the input channel or the input channel closes. And again, we just return. And I'm using named input parameters here. So they get instantiated as their 0 value when the function starts. So you haven't modified any of the values here. So return will just return 0 and false. And again, false means that we're not OK. And we do that because the context has been canceled. Then in the second case, we are modifying the val and OK return parameters. So if an actual value is received from the input channel, then we'll be returning that value and true. And then if the input channel was closed, we'll be returning 0 and false. And check out how much better this implementation is. So much simpler and also easier to test. And I also like it because using it looks a lot more similar to using the CancelOrSend helper. So instead of doing this select statement here, we're going to do val OK equals CancelOrReceive better, pass in the context and the input. If not OK, we're going to return. And then we can proceed with modifying the input value, doubling it in this case, and sending it to the output channel. And now if we run this, we're using both the CancelOrReceive better and CancelOrReceive official implementations. We should get the same output that we did before. Cool. So these basic helper functions are super useful for one-off select statements. But for pipelines specifically, I like doing another abstraction on top of these that will clean everything up even more. So instead of spinning up a Go routine in each of the pipeline functions, we're going to have a generic run function that will do that for us. The run function will have two generic types, one for the input type and one for the output type. And we use two types because it lets the transform functions that you pass into run output a different type than they take in. So then the function will again accept a context and an input channel, and then a transform function. The transform function takes in a input type and outputs and output type. Then we will return a channel. So the implementation of this function will look super similar to pretty much everything we've done this far. So you're probably getting pretty sick of this pattern by now. But we make the output channel, and then we're going to start our go routine. And the first thing we do is defer closing out. And then we have our for loop. And first we want to try to receive from the input channel. So we'll use the CancelOrReceive function, pass in the channel, and then if this is not okay, we're going to return. Then we're going to call the transform function on the value. So we get our output value by calling transform, and then we want to pass that new output value to the output channel. So we can use the CancelOrSend function, pass it the context, the output channel, and the value we want to send. And then if that doesn't work, we're going to return. And lastly, we need to return the output channel. And that is it. You can also do the full for select pattern here if you want all the code in one function instead of spread out like this. All right, so the generate stage has no input channel, so it stays the exact same. But for all of the other pipeline stage functions, we can change them to just be simple transform functions. So square will take an int in and return an int. And all it's going to do is square the input, print what it's doing, and then return the squared value. So we can get rid of all this. And that is so much nicer. And then the double function, same thing. We're going to double the input, do a print line, and then return the doubled value. So this looks way better, and it's also way easier to test because it takes the context and go routine logic out of your transformation functions and just lets them be transformation functions. And then in the main function, when we're setting up the pipeline, instead of calling square or double, you call run directly. And you pass in the context, the upstream channel, and the transform function. And then same thing here. We're going to run the context, the upstream channel, which is channel 2 now, and the transform function. And like I was talking about earlier with the 2 generic types, we can add another stage that takes in an int and returns a float. And here we'll just return float 64 conversion of the int plus 0.5. Then we wire that up in the main function in the exact same way. And now when I run this code, it should all work. Yes. Cool. All working. All right. There's one other really big reason I like using a run function for pipelines. It makes it super easy to spin up multiple worker go routines to run a single stage. So let's say our square function is a CPU bottleneck. It takes a bunch of time to do. So we'll simulate that with time.sleep for a second. And I'll change this to like 4. So now when we run this, we get the output, but it comes super slow. So what we want to do is run the square stage multiple times in parallel using different go routines. And to do that, we just need to adjust the run function a bit. So first we're going to pass a new parameter to it called numWorkers, and it's an int. And that's how many go routines we're going to spin up to run the transform function. I'll also add a quick check on the numWorkers parameter. I panic here because I like to hard code all of the numbers I put in to tune the pipeline, but you can also just return a nil channel and handle it that way. Now, because we're going to be spinning up multiple go routines, we need a wait group. And we need that because we need to wait until all of the go routines have exited before we close the out channel. Otherwise, one of the go routines might try to send a value to the output channel after it's being closed, which would cause a panic. So now we spin up a bunch of Go routines according to the num workers variable. And then we'll use waitGroup.go to actually start the Go routines. The Go routines will be pretty much the same as before. We're just not going to defer closing the output channel. So it has the same loop, doing the same thing, just multiple Go routines running. And now, because we need to return the output channel, we need to wait on the wait group to close the out channel in another Go routine. So we'll do go func and wait group.wait. Then after that, we want to close out. So once all of these Go routines have exited, then we will close the output channel. So now when we configure our pipeline in the main function, we can pass in how many workers we want running. So for square, let's say 10, double just needs 1, add half just needs 1. And if I run this again, we get way faster output. Cool. One caveat with the worker pattern is that it destroys the ordering of values from the input channel. So if you need ordered values, it's best to not use multiple workers, or you can use a custom job type that you would pass to the channels that has a sequence number, and then you could add another stage that does reordering. Okay, the last thing we need to add to the run function to make it uber complete is a way to buffer the output channels. So all we're going to do is add another input parameter. And then when we make the output channel, we'll use that input as the buffer. The only awkward thing about this is that it applies to the channel that's going into the next step. So if I say the buffer for the channel coming out of square is 10, that means the channel going into double will be 10. And it's double that really matters for this buffer. And if you want to buffer from the channel you get from generate, I would just do that manually. So this is my ideal setup for a linear pipeline. But what happens when you split the pipeline up? For example, if you have transaction data from a purchase and you need to pass that data to both a fraud detection pipeline and a transaction processing pipeline. The flow would look something like this, where we have our pipeline, and then at some point we copy this channel. So we have two duplicates, and we can pass both of those into separate pipeline stages. Some sources call this the fan out pattern, but other sources call just using workers the fan out pattern. So to avoid confusion, I just call this split channels. There are also a lot of mentions of the T channel pattern on the internet and in the Concurrency and Go book. And it's basically this split channel pattern, but it's limited to 2 channels instead of an arbitrary number of channels. And the implementation in the Concurrency and Go book doesn't account for one of these forks being slower and blocking the other one. So we'll fix that. The fact that Go channels don't have a way to do this natively is one of the most annoying parts about them, in my opinion. So hopefully they add that in the future, but for now, let's hack our way around this. So we need to duplicate an input channel into multiple output channels so we can broadcast the data to separate pipeline stages. And we'll write another custom helper to do this, and I'll call it split. It will have one generic type. And again, it accepts a context and input channel, the number of channels you want to split it up into, and the buffer you want each channel to have. Then it will return a slice of receive-only channels. The general idea here is that all the values in the input channel will get copied into each channel that we put into the slice that we return. And then you can use each channel in the slice with a different pipeline, effectively forking the pipeline. So let's do the implementation. First, gonna check that num channels is not less than 1. And then if the buff is less than 0, we're just gonna set it to 0. Okay, so now we need a slice of channels to populate and return. So we're gonna make a slice of channels with type T, and we want the length to be the number of channels. So we have the slice, but we need to put channels into it. So we're going to range over the slice and put a channel in each index, with the buffer being the buff that we passed in. Next, we spin up a Go routine that will be responsible for reading values from the input channel and passing them to all the output channels. So first, because we have multiple output channels, when this Go routine returns, we need to close all of those channels. So we're going to defer a custom function that will loop over the channels and close each one. Then we'll do that same for loop that we've been doing this entire video. So first we'll try to receive from the input channel. And then this next part's a bit different because we need to send that value to all of the output channels. So we're going to do for loop over the channels and do our same CancelOrSend. Cool. Now, this is an important point to understand. So long as none of the buffers in the channels fill up, this send will never block. But if even one of the channels has its buffer filled up, then this will block. And then you'll have each fork in the pipeline waiting on the slowest fork. So if you're going to use this pattern, it is super important to tune the buffer size and how many workers you're using to make sure you never run into that issue. Okay, one last thing for this. We can't just return the channel slice that we already have because we are returning a slice of receive only channels, and this slice is a slice of regular channels. So we need to make a new slice of receive only channels of type T. And then again, we're going to range over the original channels and set the values of the new slice to those channels. And now we can return that. Cool. So now let's use that. Let's say the double and add half functions are part of two different pipeline workflows. So after square, we need to split the pipeline here. So we're going to call split, pass in the context, the channel, the number of channels we want, which is 2, and the size of the buffer, which I'll just say 10. Now we can run double on forks at 0 and run add half on forks at 1. And now we have 2 separate final output channels. So I'll add another Go routine here that will just range over the first channel. And this one needs to range over the second channel. Change this to output 1 and change this to output 2. So now when we run this, we should get output from both parts of the pipeline. So we're getting both output 1 and output 2. Okay, the very last pattern, I promise, that I want to cover in this video is the opposite of the split pattern. It's when we have 2 or more different channels and we want to combine their outputs into a single channel. This pattern is officially called fan in, but I like calling it channel merging because it's the opposite of channel splitting. And it'll look something like this. So after we split and run the pipeline separately, we're going to merge those channels back to a single channel, and then we'll have a final single output. So let's build out the last helper function to do this. I'm going to call it merge, and it has 1 generic type. Again, takes in the context, takes in a buffer size, and then a variadic inputs parameter, which are a series of channels that you want to merge together. And then we are returning a single output channel that will be the merged channel. So first we make the output channel that we need with the buffer that we want. And then similar to the run function, we're going to need a wait group for this. Then for each of the channels in the inputs, we're going to launch a Go routine that will be responsible for receiving from those input channels. First, I'll do a quick nil check. And then we're going to do our loop. And this looks the exact same as all the other loops. So we try to receive from this specific input channel. And if we can't, we return. And then we send the value from that input channel to our unified output channel. And then last, we need to wait until all the Go routines are closed using waitGroup.wait, and then close the output channel. And then we just return the output channel. Awesome. One caveat with this pattern of merging channels is that you can't merge channels that are of different types. So if I want to merge our channels from this example, I need to modify this, say add 10 to return an int as well. Cool. So now instead of having two different Go routines running that are handling these channels individually, we're going to merge those channels back together. So merged equals merge, pass the context. The buffer size doesn't really matter. It can be 0 here. And the inputs are going to be channel A1 and channel B1. And then we can get rid of this and just range over the merged channel. And now running this should look pretty similar. Yeah, good enough. Okay, and that is everything. Pipelines are used a lot in Go, so they're definitely worth getting familiar with and learning really well. And if this video helped you do that, consider subscribing for more content like this. As always, keep breathing, keep building, and I'll see you next time. Peace out.